Good evening, everyone. Welcome to Science at the Theater, sponsored by the Friends of Berkeley Lab. My name is Jeff Miller, Head of Public Affairs at the Lab, and if not exactly your moderator for the evening, one of its many, many voices, as you will see. Our topic this evening is technology, specifically the practical and inspiring technologies spinning out of Berkeley Lab that have particular pertinence to people in the developing world. A new institute at the Lab, the Institute for Globally Transformative Technologies, I know a mouthful, also called LIGHT, is helping to identify and speed into existence a variety of simple, powerful, practical, and creative inventions aimed squarely at the root causes of global poverty. Now, one of the truths that we'll hear tonight is that 98% of the donated equipment is broken within 5 years, equipment donated in the developing world. So that you'll hear tonight how LIGHT is confronting that problem as well. It's not just about bringing things to the developing world, it's about the service model and a lot of other things in addition. So not surprisingly, we think this is Berkeley Lab at its very best. And on this stage tonight, you will meet a long cast of characters who are all playing a role in the race to save lives and improve the well-being of people everywhere. As always, we will follow tonight's program with a question and answer period. Microphones are located here, and there are two upstairs as well. Lastly, thanks to all of you who happened to go to the city on October 22nd to the Herbst Theater to hear our two Nobelists, George Smoot and Saul Perlmutter, our most recent Nobelists, discuss the fate of the universe with KQED's Michael Krasny. The video of that evening is available on our YouTube site, as is the video that we showed at the Herbst Theater event, and that's called Looking to the Skies. This is the connection between the real connection between Maya astronomers and modern cosmologists. So it is now my pleasure to introduce the director of the lab's Environmental Energy Technologies Division, the man behind LIGHT, the Darfur Stove, and the recipient of many national and international awards for his humanitarianism. Please welcome Berkeley Lab's Ashok Gadgil.
Thanks, Jeff. So my job is to give you a bit of background of how LIGHT came into being. It started with the director of the laboratory, Dr. Paul Alivisaros, asking me a couple of years ago, how is this going to go on? You have been doing work about disinfecting water for the poor people in poor countries. You've invented a stove that helps women in Darfur. You now work on removing arsenic from drinking water in Bangladesh. But these are your own personal passions, and how is this going to get institutionalized? How is it going to get continuity in a way that is organized and that taps into enormous intellectual horsepower at a Lawrence Berkeley National Lab? So out of that thinking emerged LIGHT, the LIGHT Institute. And I'm going to just give as an example the kind of work that I was doing at about the time that we were thinking about how LIGHT should be structured, how LIGHT should tap into this intellectual horsepower of the Berkeley Lab, and how we could go about making a change for the better for people who live on less than $1 or $2 a day. So as an exemplar, I'm going to walk you through very quickly the work on cook stoves for survivors of the conflict in Darfur. My name is Ashok Gadgil, and what we are starting with is a map of Darfur, Sudan. The Darfur conflict started in 2003. 400,000 people, mostly men, were killed. The estimates vary. It's hard to get an exact count. The lower estimate is maybe 300,000. Higher estimate is a little over 400,000. There were 2.7 million refugees that were displaced, mostly women and children, because it was mostly the men who had been killed. And these 2.7 million people had their houses burned down, villages devastated, lands taken away, and then they streamed into camps for internally displaced people. This is what the camp looked like when we visited that back in 2005. This is a photograph from Otash camp. Each of those little huts houses a family that originally lived in a multi-room house. They had their own land and a meager existence as a subsistence farmer, but maybe with their own flock of sheep and some land which they had for generations. Now they lost everything. They got packed into these shelters. They were given food by the United Nations World Food Program, WFP, but not fuel. And they would leave the safety of the camps to, women would leave the safety of the camps to look for fuel wood outside the camps so that they could cook for their families. As you can imagine, you do this in the middle of the desert. Very rapidly, there is an expanding zone of complete denudation around the camps. And very soon, there is no fuel wood within walking distance. This is what it looked like even in 2005. Now, in North Darfur, which is even more desertified, there is no fuel within a day's walk for 80% of the people. People have resorted, women have resorted to selling their food rations to exchange some of the cash for buying fuel wood from other middlemen. And it has led to starvation, replacing the risk of gender violence and mutilation for the women as they leave the safety of the camps. We ended up, and here is a group of women returning after 7 hours walk. That is the average duration of a walk every other day. And sometimes they carry their babies on their back. You can't see it very clearly, but that's a 7-hour trek for the baby hanging on the back of the mom because there is nothing else. There's no relief there. So I was asked to figure out what to do about this. Can I do anything about this by an officer from USAID? And at that time, I didn't have an answer. So it was a huge thing that hangs over your head. You all the time think about what can you do about something like this. It's so horrific. But I eventually discovered that these people cook on 3-stone fires. And you see a 3-stone fire here in the picture. It's literally 3 stones supporting a pot, and a fire is lighted underneath. It's the most primitive way to cook. It's also the least efficient way to cook. Between 5 and 7% of the chemical energy in the wood is transferred as heat in the pot in this most primitive and most widespread way of cooking. But which also meant that maybe we could do something that allows them to keep their pots and their food and their culture and their way of cooking undisturbed, but figure out a way that allows them to cook with maybe half the fuel or 1/3 the fuel. So that's what we started to do. In 2005, they were using $1 of fuel wood daily in terms of the traded value of the fuel wood. Women were already selling food for firewood. This is what we were doing in 2005 December, comparing side by side different stoves in Darfur, 3-stone fires with number of stoves we took there because we didn't want to invent stoves. There were a lot of people who had done the stoves, so we just took some stoves which we thought would be useful. And our job would have been, hey, this is a stove that works. The USAID or aid organizations can buy them by the tens of thousands and distribute them. But that was not to be. None of the stoves we took were good enough. So we started finally designing stoves ourselves. This is a group of students, graduate students at UC Berkeley, working in a class that I taught, but specifically addressing how to make a stove that works with Darfur pots. I brought back pots from Darfur with a little fan that you see in the foreground, simulating desert wind at 5 miles per hour racing across the pot, and you see a little anemometer there, a cup anemometer between the pot and the fan. And this stove, in presence of breeze, could actually use only 1/4 of the fuel that they would have used in a 3-stone fire. Now, lab conditions are different in terms of field conditions. We had lab conditions at the Berkeley Lab, also testing for emissions of particulates, carbon monoxide, and measuring fuel efficiency in these stoves as we went along improving the stove. Here is a workshop in Darfur building the stoves that we designed. We co-designed these stoves with Darfuri women, and this is eventually the stoves that is in production now is what we call version 14 or V14 of the stove. These are Darfuri refugees, the survivors among the men who have been trained by our engineers on assembling stoves using equipment that we sent from here and assembled it in and set up that assembly shop in El Fasher in North Darfur. And now they can build, essentially this team of 12 people can build one stove every 5 minutes, as opposed to a mud stove, which they would do, a fuel-efficient mud stove, which wasn't that efficient to start with, which would take them 3 days to build one stove. And that's the difference of doing science and engineering and technology and bring it to bear on something that is as basic as cooking, but something that is as heart-rending as women exposed to sexual violence. So these are the stoves built in that assembly shop. Now, as we speak, we have more than 22,000 of these stoves in the hands of women in Darfur. We have 10,000 more flat kits, IKEA-style flat kits, which have been shipped and which are waiting in Port Sudan to clear customs. So in 6 months' time, they would also be assembled, and we would have 32,000 stoves in the hands of women cooks in Darfur. The total number of stoves needed in Darfur is only 400,000, and we would have gotten close to 10% by end of next year. There is a nonprofit called Potential Energy. You just go to potentialenergy.org, and that has lots more material about what has come out of the Berkeley Lab and is making a huge difference to the lives of women and girls in Darfur. So on the 8th of February this year, at White House, there was an announcement that this kind of work is now being turned into a systematic, organized way to take our best minds in science and engineering technology to address problems at the bottom of the pyramid, to do the last mile of research that otherwise never gets funded, because nobody votes for that kind of funding. Berkeley Lab said, we will take this on because it's important for the world, it's the right thing to do to provide a low-carbon, high-efficiency trajectory for the bottom 2 billion people to reach a standard of living that we consider essential for anybody in modern society. So that's what's announced on the 8th of February. And with that, I would like to invite the Executive Director of the LIGTT Institute, Shashi Buluswar, to come and lead the talk.
Thank you, Ashok. Thank you. So one story Ashok didn't tell you. A couple years back, I was in Sudan, in Darfur, working with the UN peacekeeping mission there. And I heard this story, which I thought nothing of at the time. And turned out there was a lot more to it than I thought. Apparently, there was this guy who'd been going to these refugee camps, building these stoves, which people really needed, really wanted, and were very appreciative of. And one of them, a family, ultimately went to this scientist and said, look, this is saving our lives. It saves us from walking 7 hours. It saves us from horrible violence. We need this. We can't afford it. We don't know what else to give you. The only thing we have is the name of our child. So they asked Ashok's name, and they named their child after him. We spend so many billions of dollars and so much energy trying to win hearts and minds, and I can't think of a more inspiring story of winning hearts and minds. And that was the genesis of the LIGTT Institute. And what we'll do today is explore a little more about what it is we're aspiring to do, how we're thinking of doing it, and we'll look at some examples. So let's get started with some statistics. And this will give us a sense of the magnitude of the problem we're wrestling with, the kinds of problems, and set the context for where these things will work. Today, in 2012, there are 870 million people who will be chronically starving. They just will not have enough to eat. Often they live on World Food Program aid. What is 870 million? That's 1 in 8 people around the world. So if this room were full, there would be 75 people who simply, on a regular routine basis, would not have enough to eat. Next, if you're a child, primary school age, there are many, many, many parts of the world where you either don't have the chance to go to school, or if you go to a school, the school systems are so broken that you might as well not go. 200 million children of primary school age. Just to put that in context, how many children is that? Well, you take all the children we have in the US of primary school age, multiply that by a factor of 3. No education whatsoever. Then Ashok talked about the refugee camps in Darfur. There are 25 million people in this year who live in refugee camps. And this is not poverty. This is significantly worse than poverty. And how big is 25 million? If you take the 12 largest cities in the US, New York, Chicago, Los Angeles, Houston, and so on, add up their entire populations, they are all living in that. In their homes are nothing more than tarp, often donated, often leaky, and they have no protection from the elements and barely any security. And then there are infectious diseases that we all hear of: HIV, AIDS, tuberculosis, malaria. And 16 million people by the end of this year will die because of these diseases. Often the medicines are there, and we'll see why it is so difficult for these medicines to reach these individuals. And to make matters worse, in large part because of things like climate change, if you think of drought and floods, these are really ravaging lots of places. Over the last 10 years, there were 158 significant incidents of drought, 16 major droughts a year, and then floods, an order of magnitude worse, 1,750. That's 175 floods every year. Now, we know, just from the last couple of weeks, that we can have major floods here. People get sick here. And a lot of people say school systems here aren't that great. So why is it such a big deal? Why is it that we worry about this in the context of developing countries? Well, it is because there is disproportionate impact on the populations of developing countries. So take the floods and the droughts I talked about. 98% of the people who suffer from this, and when I say suffer, they permanently lose their homes, right? They die, they lose family members. Think of how horrible Sandy was to the residents of New York and New Jersey. As horrible as it was, most of the devastation was economic. We live in resilient places where we're able to withstand the effects of these types of incidents and are able to put our lives back together. Sometimes it's difficult, but we eventually get there. So why? There are, here we have hospitals, we have doctors, we have technicians, we have institutions that reasonably function, we have roads, infrastructure like telecommunications, and so on. These things are missing. So if we think of what the big differences are between a developing or underdeveloped country and a country like the US, it is, number one, more often than not, the governments are weak. The institutions are not very strong. There isn't necessarily rule of law. There isn't the environment to have policy, and even if policies are on the books, they're not necessarily enforced. Next, infrastructure we talked about. So if you think of a farmer over here, it is very easy to grow something 1,000 miles away and send it all the way to Berkeley. But what if there was no road whatsoever? How could you, if you're living 1,000 miles from the nearest city, what hope do you have of growing anything and selling it to anybody? Then there's the question of technical talent, which is, don't quote me on this, but one statistic I read is when Tanzania became independent, the president, Julius Nyerere, the founding father of Tanzania, he said he had a total of 4 civil engineers in the whole country. And the country was expected to build using 4 civil engineers. I might be off on that, but it was not any more significant than that. So now the question is, in the absence of this, what do we do? Over the last 5 decades of the aid work, we invested a lot in this. Billions and billions of dollars have gone into fixing institutions. We've tried to educate. We've tried to build roads and dams. And we can still keep doing that. But what in the meantime? In the meantime, so let's say we start all over again, we invest in all these, it will take at least a generation. If we did everything perfectly, and Lord knows, things have been far from perfect in the aid industry. If we did everything perfectly, it would still take at least 1 generation of students to get educated, to learn what they need to become technicians, to become well-educated legislators, doctors, and engineers. And if we then step back and think of what a day in our life looks like compared to the day in life of a poor farmer in a typical country in sub-Saharan Africa, it is, from the moment we get up, we have technology. We have alarm clocks, clean water, automobiles, air conditioners, flushing toilets, refrigerators. And there is so much we take for granted that simply does not exist. It almost, when you go to some of these countries and you visit some of these communities, it really feels like they're living in a different century. What's worse is that if you think of R&D, research and development, every day something new gets announced that makes our life so much easier. And Lord knows, every day there are 1,000 iPhone apps, which we don't need, but we get anyway. But no one's doing R&D for developing countries. They certainly don't have the budgets. If they had the funding, they don't necessarily have the scientists and engineers. And we're not doing anything significant for them. So that's where the idea of LIGHTT came in. The Lawrence Berkeley Lab has 3,000 plus of the world's smartest, most accomplished scientists and engineers. 13 Nobel laureates in its history, and we do $800 million of research every year. Granted, not all of it is relevant to developing countries, so the Higgs boson, as groundbreaking as it was, there's a lot of theoretical stuff that isn't necessarily relevant, but a significant portion of it is. And before I took on this job, I used to work as an advisor for various UN agencies and governments and NGOs and foundations. And I would get enormously frustrated, even depressed at how ineffective that whole industry is. Sometimes it feels like the whole aid industry is an employment program for people living in developed countries. And then we got a call from the Berkeley Lab saying, hey, look, we've done this thing with the Darfur Stoves. We did this thing with, we'll hear about an ultraviolet UV water purification system. But we'd like to really institutionalize this. We'd like to see if we can, what if we, this is stuff that people like Ashok, out of literally the goodness of their heart, had been spending nights and weekends doing. This was not their day job. And the question on the table was, what if we actually created an institute? What if we worked with these 3,000 scientists and engineers and really used the muscle of the lab? What could be done with that? And we shopped this idea around. We spoke to well over 100 people in the ecosystem. And the response was phenomenal. People, the phrase game-changing gets thrown around often. That was thrown around quite a bit in that conversation because everybody felt that things, for the most part, are done on the margins. Anyone can show up and hand out medicines. It's not that hard to go build a tent. But to really bring game-changing technological breakthroughs is difficult. And what does that mean? So if you think of something as mundane and unpleasant as a toilet, right? What does it take to actually have a flushing toilet? It takes a sewer system. It takes water. And we flush our waste with drinking water. Most people in most developing countries, actually the water they drink is so much worse than the water we use to flush our waste. There is no electricity, no infrastructure, and even if all those things were there, the populations don't necessarily have the financial, economic wherewithal to buy things. So what does a breakthrough look like? First of all, it has to work in the absence of electricity, reliable electricity anyway. Number two, it has to be hugely affordable. Number three, it has to be robust. And even if we do all of those things, it's not like there's a Walmart that we can send these things to, right? There is no mechanism for distributing these things. And so that's what we have to do to come up with breakthroughs. And so our model is, our motto is, we identify, we discover, we develop, and we deploy scientific and technological breakthroughs for sustainable global development. And over the course of the evening, we'll see how this motto manifests itself in actual technologies. But it's, roughly speaking, got 4 parts to it. Number one, we have to know what we should be focusing on, because there are 1,000 technologies out there which look very nice, but ultimately don't solve the problems. More on this later. Then, once we figure out what we want to do, we look in the lab. And I said $800 million buys you a lot of research. So we see what research has already been done. And recognizing that the research here is all for US-centric needs for the most part, anyway, we have to figure out what research is almost done, and then just do the last mile of research. And think about the leverage this offers, because we'll talk about that lovely box. It's a surprise. I won't tell you what it is. You'll find out soon. But we'll spend a few seconds talking about why we were able to develop that with as little money as we were able to. So leverage, which is all this research has been done for purposes here. Can you tweak it a little way and apply that to solve these significant problems in other countries? Then once we do the core technology, chances are that product A in one country will be used very differently from another country. It'll be used very differently in a city versus a village. And it's very important to engineer and design these products so they're actually, they're serving the needs of the users. They're robust, they're inexpensive, and we also have to think about the repair infrastructure, right? So there's got to be, let's say we come up with the perfect widget for something. What use is this if it breaks down in a year and no one's there to repair it? So we have to think about all of those things. And then finally, we have to figure out how to deploy this. We all know by now that the old model of let's just give those poor people these technologies, let's donate them, that has failed over and over and over again. So we have to be very creative, very thoughtful in how we actually deploy these using business models that make sense for the particular context. So that's how we're loosely thinking about the LIGHT Institute. And we've been around, so the announcement was made in February, but we hit the ground, I think, in April. So it's been about 8 months we've been in business. And here's what we've done so far. First of all, there are a few really interesting technologies that we know are important and interesting. There's huge demand for. And we have a small portfolio of those projects, and we'll see 4 examples of that today. Then we're stepping back and saying, what really matters? What are the most critical scientific and technological breakthroughs that are required for solving these problems? And once we do that, we'll have a good sense of what matters, what doesn't matter, where we should focus. So with that in mind, let me now invite my colleagues, Zach Friedman and Lena Vashi, who will talk about the 50 most critical breakthroughs required for sustainable global development.
So Shashi mentioned this idea of a breakthrough, which begs the question, of course, why are we so interested in these breakthroughs, and what is a breakthrough? And the answer, at least for me, is there's tremendous power in these breakthroughs. Global development is extremely complex, and there are many problems within development that technology is simply not applicable to. But there are many, many problems where technology is a key component of the solution. And oftentimes what we see within these problems is that when the right technology is developed, we can have a massive and rapid impact on people's lives. Prior to the mid-1950s, for example, hundreds of thousands of people around the world were affected by polio, which is a viral infection that infects the spinal cord, the brain stem. It can affect higher functioning within the brain, such as motor control. And this was pervasive. It was everywhere. The idea or the image of a child who needed an iron lung to breathe was something that was iconic. In the mid-1950s, we developed an oral stable vaccine that allowed us to take this disease that we couldn't even control in the US, that was one of the wealthiest countries in the world, and effectively eradicate it in many of the poorest places across the globe. Another, potentially even more interesting technology comes from Asia, where again, in the 50s and 60s, large parts of the continent were facing massive starvation. It's almost amazing to think about when today we think of Asia as this global growth engine. But for a long period of time, large parts of this region were actually dependent on food aid. That was solved in a large part to breakthroughs such as what we're looking at now, which is a semi-dwarf variety of rice, which essentially creates much more grain per seed, and also has a shorter stalk so that the stalk itself doesn't bend over and break under the increased weight of the grain. It was breakthroughs such as this that enabled the Asian Green Revolution and essentially allowed the continent to double its food production in the course of just a couple decades, which is tremendous, essentially eliminating food security for a large portion of the population. Now, it's easy for us to look back and say, okay, this was a really important breakthrough, or this was also a really important breakthrough. But as an institute, as LIGHT, we're forward-facing. We want to know what we need to be investing in. And we want to know what we tell our partners, oftentimes who are funders, who are interested in funding this type of research. So, for example, should someone be focusing on a low-cost treadle pump that allows you to pull water from a river to spray on fields? Or should we be investing in development of drip irrigation technologies so that we can more effectively spread the water across the fields? Should we be developing microbes that will help decompose fecal sludge in open sewers and urban slums? Or should we be developing a new generation of toilets that will prevent that fecal sludge from ever getting into the environment? Should we be developing personal or household water purification systems? Or should we be focusing on technologies that work at a community scale? For us as an institute, our focus is on having the greatest impact as possible, which means one thing: we're focused on the problems. And this might seem very straightforward, right? If you want to solve something, you focus on understanding what that problem is. But it's not necessarily the nature of all scientific research. If you think about it, oftentimes the way that research institutions are set up, there are incentives for scientists to know a lot about broad areas, but really focus on individual areas, and that's where they push, and that's where you create science, and that's where you create these insights. The implication of this is really interesting, because oftentimes when we find science and technology being applied to global development challenges, the solution was actually developed before the problem was really understood, or in often cases before the people developing that solution even understood that the problem existed. So this is something that we're very cognizant of at LIGHT, and it's a paradigm that we refer to as hammers looking for nails. When you're a hammer, everything looks like a nail. And it's amusing, but it's also challenging, because from our perspective, this is part of the reason why oftentimes technologies that are high potential never quite live up to their expectations. So instead, we go back to the problems. And for us, we've defined the problems in 8 core areas with 3 themes that cut across each of these. And what we do is we essentially look at a single area and we unpack it, and unpack it, and unpack it, and unpack it until we get down to individual addressable problems. And only then do we say, what is a technology that can solve this issue? So to illustrate a little bit of what this is like, let's look at one of the most important challenges facing the global health community today, which is maternal health.
It has been said that the most dangerous thing an African woman can do is give birth. So what is the problem here? 1,000 women die in childbirth every day. That means that by the time this presentation is over, 50 women will have died. 1 in 39 of all African women will die during pregnancy or childbirth, and most of these deaths are from causes that are treatable and avoidable. So how do we solve this? Solutions can be based on policy, behavior change, financial inclusion, and technology. For the purpose of sticking to LIGHT's mission, let's focus on the technological interventions. So how can technology address the issue of maternal mortality? When talking to doctors, they'll highlight the need for antenatal care, the importance of getting mothers into clinics, as well as a host of technologies like the portable ultrasound, hemoglobin detectors for anemia, uterotonics, sterile delivery kits, and blood pressure monitors. But with so many options and recommendations, where do we begin? It is essential to start with the problem. And if the goal is to reduce the number of maternal deaths, the obvious question, of course, is what exactly is causing these deaths? Well, here's our answer. While there's no single dominant cause of maternal mortality, postpartum hemorrhage is overwhelmingly more than 1/3 accountable for maternal deaths. Let's take a closer look. Postpartum hemorrhaging, at a closer glance, is clearly a very complex issue with its own entire set of underlying causes. In this case, however, we do have a single dominant cause, which is uterine atony. Uterine atony occurs when the uterus fails to contract enough to reduce bleeding after the delivery of the baby and the placenta. While we don't know exactly why this happens, we do know how to prevent it and we do know how to treat it when it's happening. There's a procedure called active management of the 3rd stage of labor. The 3rd stage of labor is from the time of the birth of the baby to the delivery of the placenta. This is a method we use in the US to virtually eliminate all deaths due to maternal mortality due to uterine atony. A key element of this is the use of a uterotonic. A uterotonic is a drug that causes the uterus to contract. In the US, we use synthetic oxytocin, which is extremely effective. Oxytocin is a naturally occurring hormone that the body releases towards the end of pregnancy in order to stimulate the uterus to contract, facilitate labor, and reduce bleeding. However, in the case that the body fails to release sufficient amounts of natural oxytocin, synthetic oxytocin can be easily administered to stimulate uteral contractions and reduce bleeding and prevent excessive bleeding or uterine atony. However, there's a catch. Synthetic oxytocin requires refrigeration, and as you may know, refrigeration is not a resource that's readily available in the developing world. As you may also know, the majority of women in the developing world do not give birth in hospitals or clinics, but rather at home. In fact, 2/3 of women give birth at home. Here we have a refugee home in a refugee camp where some of our colleagues have actually worked, and this could be a typical scenario for where a woman would give birth. So as you can see, there's no option for electricity or refrigeration, thus making synthetic oxytocin not exactly a realistic option for the majority of women in the developing world. So what is it that we need? What we need is a thermostable uterotonic that can be administered easily with minimum to no training. This uterotonic could be a stable version of oxytocin or another uterotonic drug. Misoprostol is a currently existing drug that's a viable option to be used as a uterotonic. However, it's controversial because it can also be used for medical abortions, and thus in some countries faces substantial political opposition. So at the current moment, the best bet for combating maternal mortality is another stable uterotonic that can stimulate the uterus to contract and prevent postpartum hemorrhaging and uterine atony. This, to us, is a critical breakthrough for global development, and this is how we go about approaching our analysis and identifying critical breakthrough technologies.
So if a stable uterotonic is what comes out of this analysis, if looking at what causes mortality and what are the subconditions and what are the issues that then drive that has led us to this one technology, the question is, what about all of these other things that have come up? So a portable ultrasound is an interesting technology, but it doesn't necessarily address any of the major issues that we identified earlier, such as postpartum hemorrhaging or hypertensive diseases. It does have an interesting property in that it helps bring women into clinics, but from our perspective, that's not enough to make this one of the most critical technologies that needs to be focused on. Blood pressure measurement devices are a little more challenging. Understanding a mother's blood pressure is a key component to diagnosing and then treating for hypertensive diseases. But there are two problems with just looking at a blood pressure measurement device on its own. The first is that it's strongly dependent on strong antenatal care, which, as we know, is not available and not available within the systems in most developing countries. The second is that hypertensive diseases are actually incredibly challenging to treat. Even in the US, the definitive treatment for mothers with extremely high blood pressure is to deliver the child. If our basic care here is so dependent on delivering a child, even if it's premature, to save the mother's life, you can imagine that there's very minimal options for mothers in emerging markets where they simply don't have access to the same type of health care. Sterile delivery kits are not as important in our perspective. Yes, it is important to have clean kits, but as we saw at the beginning, infections only account for about 8% of maternal mortalities. We do see this come up again when we look at neonatal mortality, where clean delivery kits are an important reason to prevent infections. But if you're thinking about maternal mortality specifically, delivery kits are just not as important. The last and potentially most challenging point is looking at hemoglobin detectors, which test for anemia. And this, similar to a blood pressure measurement device, is really most effective when there's strong antenatal care, which we know there isn't. What's even more challenging is it's complicated to understand the link between anemia and hemorrhaging. When most maternal mortality that's due to hemorrhaging, the actual cause of death is blood loss, as opposed to deprivation of oxygen, which anemia contributes to. And so it's unclear that even if you treated mothers for anemia, if it would actually improve the outcomes for mothers who hemorrhage. From our perspective, if you look specifically at saving mothers' lives, there's one clear technological breakthrough that stands head and shoulders above the others in terms of the impact that it can have, and it is a stable uterotonic. So this is something that we do repeatedly. It's a complex way to analyze a problem, and it's somewhat time-consuming, and sometimes it's frustrating because you have a huge set of problems, and you come up with maybe one or two technologies that really seem high potential. But at the same time, it's replicable. And fortunately, with the help of a large number of experts, we're going through this list on an individual basis, breaking each issue out, understanding what underlies it, understanding what contributes to it. We're about a quarter of the way through now, and we hope to be done by July. So if we're lucky enough to be here again, hopefully we'll have much more to discuss with you. Thank you.
Thanks, Zach. So the reason we're doing this is we could simply go ask people, ask experts, what do you think the most important breakthroughs are? And what we found is that the answers are not often correct because there's always the syndrome that Zach talked about, which is a lot of experts like their own hammers. And so it's really important for us to push the boundary in terms of, well, let's step back and really unpack and unpack and unpack. And it's OK to cross out some sacred cows. Without doubt, some of our findings are not popular. But what we're finding is that no one's actually done this kind of analysis before. And so once they see the fact base, once they see the analysis and the logic, what we're finding is that a lot of the experts are coming around. And what we're hoping to do with this is two things. First of all, as Zach mentioned, the general level of understanding of this question, which is what are the most important breakthroughs, is actually not very high. And so part of this, one objective is to use this to coalesce and catalyze the ecosystem. So there are a number of organizations like USAID who are really interested in this because they want to use this to shape how they fund. And so what we'll do with this is an annual, so once we identify the 50 breakthroughs, we'll have an annual state of the breakthrough event where we say, what have we learned? Have we developed anything new? What are the technical challenges we have overcome and need to overcome next time around? And once we solve a technology problem, how do we think about the deployment? What have we learned there as well? So we're finding that there's a lot of excitement and a lot of interest in this particular exercise. And then what does it mean for us? So once we identify the 50 breakthroughs, think of a timeline. Some of the stuff can be done by next year. Some of the stuff is 10 years out. And so if you think of these 50 bubbles representing these breakthroughs. They'll be stretched all along that timeline. And let's say you draw a line in the middle, 5 years. Frankly, if something is a year out, chances are someone else is going to do it. We don't need to do it. We don't need to, it doesn't make sense to use, it's an overkill to use a national lab's capacity to do that. So we're focusing on the stuff almost at the other end of the spectrum, which is if something is really, really important, will save a lot of lives, but is 10 years out, can we accelerate that? Can we make that happen in 2 years? Frankly, nobody, as I said, I've served in my old jobs, I've served institutions all over the world. I very strongly believe that the Lawrence Berkeley Lab is the single largest repository of R&D to solve these problems and to accelerate these breakthroughs. What I'll do now is I'll go pick up that box, bring it here and tell you what it is, and then introduce my colleagues. Feel free to guess what this is. Oh my gosh, great guess. So this, my friends, is the world's first portable, solar-powered vaccine refrigerator. And to tell you why it's important and how it works, Jonathan Slack and Reshma Singh.
Okay, so before we start, I want to acknowledge one member of our team who's not up here with us, and that's Howdy Gowdy, who is a very essential designer and heat transfer expert who made great contributions to this. And there will be a moment when I have to put this back. Okay, so we're queued up here. All right. Contrary to what most of us would think, this was not the idea of the FBI. This was first published in the Washington Daily News on February 7th, 1949. And FBI Director J. Edgar Hoover was hesitant to allow this to happen, but he decided to take the risk at the urging of these two editors of the paper. And within a year, 3 of these men were apprehended based on tips from the public. And after that, he was a convert. And starting on March 15th, 1950, he began publishing directly himself. So what these people have in common, what they still have in common if they make it onto this list, is that there's no ambiguity about the threat they pose to society. If you see one of these people, it's clear that you need to take action today, not tomorrow. These are some of the world's and humanity's most feared and most persistent pathogens. We have polio, tuberculosis, rubella, measles, diphtheria, tetanus, mumps, pertussis, yellow fever. This last one's the hantavirus. And what vaccination does is to give our immune systems an early warning, a heads up. The message is, if you run into one of these, if you see one of these, do not be polite. Do not make small talk. Do not pause for even a moment. This is the moment to mount a defense, to take every resource you have and to do it in the biggest way possible and to do it immediately to fend off one of these. Now, oops, went too far. Okay, so we've come to take for granted our very effective immunization programs. Okay, we take our kids to the doctors when they're little. We take them every few months, and they get a whole bunch of shots. And by the time they're 5 years old, we pretty much have passed the point of anxiety about the health of our children. We have new things to worry about. They go off to school, and you have to worry about how that's going to go for them. But infectious communicable disease is pretty low on our list, all right? And it's been this way for several decades, many decades. But I think there are probably people in this audience tonight whose parents, and maybe even some of their childhood friends, were actually affected by diseases that we almost never see here in Berkeley anymore. So this got me curious. I called up the Berkeley Department of Public Health, and I was fortunate enough to reach Dr. Jose Ducos, and he invited me down. We went through his old record books. He had actually, as a result of this call, he discovered some books that he hadn't actually found before. And up here you can see, this is Berkeley, California, all right? And what we discovered was that back in the 30s, and this was when Ernest Orlando Lawrence, who founded Berkeley Lab, was working on his first cyclotron. This was before he got his Nobel Prize in Physics in 1939 for that cyclotron. At that time, the beginning of summer, which most of us think of as like really exciting time, especially if you have kids, they get out of school, the beginning of summer had an edge of terror to it that we can't imagine today. In June of 1933, 42 people in Berkeley came down with polio. 812 people had pertussis. That was 1 out of 100 people in the city of Berkeley, which had a population of 82,000 at that time. And most of these were kids, and for the kids, it would be a life-threatening illness. And you can imagine there's a lot of miserable households, 1 out of 100 households in Berkeley at that time. 2,400 people altogether in Berkeley suffered from diseases that caused either debilitation or incapacitation and required the energy and resources of the people who cared for them. That was all just in 1933. But in many parts of the developing world, that kind of burden on the community and that kind of suffering of people who still get these diseases, it persists. And Reshma is going to tell you about that.
Well, the 1930s may have come and gone in Berkeley, but it still persists in many parts of the world. In fact, on my last visit to India, I wasn't really surprised to see many centuries living together. I saw a Mercedes-Benz and a bullock cart parked at the same traffic light. This is the kind of things that happen. There's a stark contrast between the developing world and the industrialized world. In fact, this contrast is even more stark when you look at the urban-rural divide. The people in remote areas, especially in rural areas in many parts of the world, don't have access to infrastructure, to electricity, to transport, to medical services, to education services. Some of these remote places are really the most pristine natural landscapes ever known to man. I mean, think of the hot sand dunes of the Sahara, or think of the upper reaches of the Himalayas, which are freezing cold. Yes, they're beautiful, but do services reach them? No. Let's take an example. If you and I had a stomach upset and a diarrhea, we would just think it's a minor inconvenience and we would forget about it in a couple of days. But a very virulent form of diarrhea called rotavirus is very prevalent in parts of Africa. Rotavirus kills 1.5 million people every year, especially kids under 5. And these are more numbers than AIDS, malaria, and measles put together. 40 Zambian kids die every day because of this rotavirus diarrhea. And rotavirus is actually vaccine preventable. Meet Lara. She grew up outside of Beira, Mozambique. She's a very bright child. In fact, she was the hope of the future for the village. Her parents took extremely good care of her. They skimped and they saved and they sent her to school. They gave her all the vaccinations that she was supposed to have. She was the first child in the village to go to college in Beira. When she was in college, one day she developed fever and muscular paralysis. And she was diagnosed with paralytical polio. Why did this happen? She already got the vaccines. Well, Lara's parents vividly remember the day when Lara was about 3 years old and they took her to the clinic. It was actually a makeshift mobile clinic under a tree in Beira. Her mother had actually taken, with great difficulty, she'd taken time off from work. They waited for the healthcare worker to come. He did arrive on his bicycle with an ice box, with the polio vials in his ice box. Lara, at 3, did get the vaccine. She got the booster doses as well. So then why did this happen? Why did she get polio? Well, in retrospect, they realized that it was a very hot, dusty day that day in Beira. Either the polio vial got overheated because of the ambient heat, or it got frozen sitting next to the ice in the ice box the healthcare worker had provided. And because of either this overheating or overcooling, the vaccine lost its potency, and despite all of the efforts of the government, the healthcare workers, the parents, the children, everybody in the chain, this still led to a devastating effect. She did still get polio. When we work with our partners in field and other NGOs and institutions like the Clinton Health Initiative, with PATH, with Gates, we realize that these kind of stories are very common all over the developing world. In fact, there's a few different patterns that are emerging. One is where the healthcare worker tries to enlist parents to come to the vaccine campaigns, which happen either monthly or weekly. The problem is that surveys have revealed that parents, even though they come to the vaccine campaigns, often find that there's unavailability of vaccines, and this is mostly because the vaccines have not been kept in a thermally safe environment, so they don't come back again. The other pattern that's emerging is that the healthcare worker will trek for miles with his ice or her ice box, find babies out in the village or in the forest. You can see this gentleman is helping a woman put a load of firewood down and inoculate the baby. This is the kind of ice box that he carries. And then the baby's vaccination is tracked by putting a little marker on his nail. That's the kind of tracking that you have. This is the use case scenario which actually shows how the vaccines are taking the journey from the manufacturer all the way to the end of chain. So let's just look through the journey of a small vial of polio costing about 11 cents, and it takes about 11 months of journey to go from the national level storage depot through the state, through the division, through the public health outpost, and then add to it some more months before it reaches the final end of chain. Now, throughout the life cycle of this vial, before it gets inoculated into a baby, it must retain a very narrow temperature range of between 2 to 8 degrees centigrade. And this is called the vaccine cold chain. And because of these kind of transportation and this kind of end-use scenarios, we have to very carefully figure out what it is that will take the vaccine all the way from lab to jab. So the WHO actually substantiates this kind of user case scenarios. In fact, with all the money being thrown at the vaccine problem, billions of dollars being spent on development and deployment, all the charity that's going into it, it is not the money which is the issue. It's actually the vaccine cold chain which is a major issue. 44%, almost half of the issue arising, the biggest barrier to dissemination of the vaccine program is the immunization system and basically the cold chain. So the LIGHT vaccine team at the lab decided to look at the critical specifications required for the last mile, where you could actually take a portable, robust, lightweight vaccine refrigerator and make sure that the thermal stability remains constant. And this was a challenge the LIGHT vaccine team took upon, and Jonathan will walk you through that.
Okay. So I'll take a few minutes to tell you a little bit about our design process. What you see here in this image, this is Howdy and me at our brainstorming old-fashioned chalkboard, color chalk. And at the advice of our legal team, we've had to obscure the images here so you can't actually interpret them so well. Howdy and I actually can draw quite well, but you're not going to be able to tell it from this. So the design process started out with some really easy to grasp parameters. We knew we had this 2 to 8 degree temperature range that we had to stay within, okay? We knew that the regions of the world that we wanted to be able to make a difference in tended to be very hot. And the WHO, the World Health Organization, has this climate zone called hot climates, and the presumption for any type of device that is going to operate there is that the ambient temperature is going to be 43 degrees C, that's 109 degrees Fahrenheit, day and night, all the time. Okay, and that's quite a challenging environment to try to keep things cool or cold inside of. So we had that information, and what we needed to do, and this is kind of unique to the LIGHT projects, you'll see in a later picture that many of us also work on more traditional scientific projects, and this project requires the ability to gather information from much more distant points, not just points of the world, but over a much broader spectrum of considerations. I mean, there's sociological considerations. It's a much more complex process. And in the process of trying to gather information, it became apparent that we didn't know what exactly we were going to come upon in terms of what would work best. It was, as you looked at those pictures, you see sometimes people are transporting these vaccines on their bicycles. Sometimes they're walking with a little cooler down little paths, you know, long distances for a day or two. Sometimes they have a vehicle. So it wasn't clear if we needed a small volume or a larger volume or a really large volume. One of our ambitions, and this is something that isn't done currently, was to make it possible for end of cold chain clinics, like very close to the very, very end of the whole system, the most remote places, to be able to keep the vaccines for weeks on end. Because right now the way it works is they send somebody out with one of these passive coolers, and they get there and they have a clinic, and if you don't make it at that time, you miss it, all right? And if you make it an hour late, and a lot of these people are walking from great distances, you miss your opportunity. So if we could make it possible to keep the vaccines cold for weeks at a time between the delivery times, that would be something really new. So we decided that we wanted our vaccine cooler to not just be a transport system, but we wanted it to also be able to store the vaccines at the end of the cold chain. And we wanted it to be able to do it with no grid power, all right? Because at these locations, you're not going to have grid power, and if you do have it, it's going to be very intermittent. And so that meant that we had to source our own power. Solar power was the most logical thing. We had to think of a cooling system, because we need active cooling now, and we need to be able to maintain this system for days at a time when there's no sun, or you might have to travel for 2 or 3 or 4 days to get there, all right? The World Health Organization requires a 3-day holdover time. That means that you can go without power. They actually allow you like 5 or 10% of solar ambient, which isn't enough to do very much with, so I just consider it without power for 3 days. But we realized that we needed to go longer than that, so we set our design goal to be able to go for 5 days with no power, and then we wanted to be able to run on a single, fairly large, you know, the newer type of solar panels is about 1.2 square meters. We wanted to be able to run on that amount of power, and we had to not only store the energy that would be used to keep the vaccines cooled overnight, but we had to store enough energy so that they would be able to go for a few more days without sun when that occurred. Okay, so we had all these design considerations, and we tried to wrap them all into a product. And what became apparent is that we really needed to be thinking in terms of a family of products. We needed to be thinking of a way that the vaccines could be moved from one system to another and carried by somebody in a backpack in some situations, carried by somebody in a bicycle in another situation. And what this led us to was a modular design. We wanted a system that could be one size for individual product, but that the core of it, the actual cooling system, could be scaled up or down to meet these different needs. All right? So what we started with is what you see here. This is a 15-liter capacity. Now that box is a lot bigger than 15 liters because it has a tremendous amount of insulation around it, because we wanted to keep our losses, or the steady state flow of heat from the ambient environment down to around 6 or 7 watts. Okay? And to do that, you need to have a tremendous amount of insulation. We needed our system to be robust and lightweight and relatively inexpensive. And in addition to that, we wanted to be able to make it available in situations where the current technology is just too expensive. So the whole system had to be less expensive, not just the individual components. And we wanted a typical healthcare worker, which tends to be a woman. Now, before you lift that up, Reshma, this is the first time she's ever lifted this up. Right here, just at this moment, you saw it, because we were putting this together until just about an hour ago. And there, that was it. I didn't actually know how that was going to go off, because she had never picked that thing up before. So those are some of our design considerations. And the thing that I feel most enthusiastic about is the fact that I think we've succeeded at coming up with this modular design. It's modular also in terms of how the vaccines are handled. And I can't give you all the details on that because of these legal constraints that were put upon us, which is not something that LBL people are used to. We usually share everything. But you will see probably in the next few months more information coming out. Okay, so that was the design process. Now, what you see here is an image of a different project I worked on because I wasn't allowed to use the actual image of the insides of our vaccine refrigerator. But you go through this process where you create these nice CAD models, and everything works so well when you're doing it on the computer. It all fits together, and all the parts are perfect. This image up here is real. We did heat flow analysis to make sure the temperatures where the vaccines are stored would be in the right range over a range of exterior ambient conditions. We can't assume it's always 43 degrees outside. It's going to get colder than that. We just have to be able to handle it when it is, but we also have to be able to handle the colder temperatures as well. So there are several iterations of this, and as we got more information from the field, from our partners out around the world, we made a bunch of design iterations, and we ran through the different thermal analysis. And then we finally got to the point where we could start building something. And this is the really satisfying part. This is where you find out, well, if you have experience with this, you know that the model always looks great and everything works perfectly. But when you actually have to start building the things, you run into little problems that you have to fix. And it's very satisfying, though, to turn it into three-dimensional reality, okay? And these are just some pictures along the way that I figured I could show you without violating our intellectual property concerns. And so this has been going on for several weeks, and we're very close to the point where we can start testing the system now and demonstrating that it can do what it was designed to do. And there's one last thing I wanted to add about this, which is that one of the great things about working on these projects is that almost everybody you run into along the way, because you're always asking for help or you're asking for resources, there's a wellspring of goodwill that comes up when they find out what the project actually is. And so in this case, for example, all the guys in the main shops, this is Steve Ferreira, that's Marty Martinez's arm up there. These guys were booked through the end of the year. They didn't have any time left. But they all figured out a way to make the time to help us out to make some of these components for us. We had vendors who were willing to drop their minimum orders because we have a pretty small budget we're trying to do this on. And we also had scientific advisors who are happy to step in and offer their expertise pretty much at no charge because they wanted to participate in this. And friends of friends who would call people different parts of the world to get information that we needed. So it was a really great feeling that everybody kind of stepped up to help out and to do what they could for their community. Do you want me to do it for you? Or are you going to do it? Okay.
So as Jonathan mentioned, that the LIGHT team really responded to the call for action, literally. So this is one of the vaccine campaigns out in Africa. So one thing that we did realize is that every country has a different cold chain, and we have to work very closely with the ministries of health to make sure that we're able to tailor our solutions. So the idea that we've always been told by the ministries of health is do not give us a product, don't give us dysfunctional stuff. We have storehouses full of solutions or products which haven't worked. So we're trying to enable an end-to-end solution for the vaccine cold chain, which means both the ecosystem as well as a product. So in terms of thinking beyond the box, right, thinking out of the box, which I guess LBNL is actually pretty good at, that's really our attitude, we want to make sure we were accountable for what it is that we're taking to the field. So a couple of things. We are going to put some temperature tracking and monitoring systems so that we can centrally monitor the system and make sure, identify that if any particular unit is not working properly, you should be able to replace it, maintain it, and service it, and also be able to do tracking of what children are getting immunized better than what the marker was doing on their finger. The ministries also realize, and the world realizes, that you can save deaths from happening. You can, over the next 10 years, be able to almost decrease the illness of about 500 million people. In fact, scaling up vaccines by 90% is going to enable $300 million of healthcare costs being saved and up to $17 billion of productivity increases. However, for us at LIGHT, The main thing is to be able to put a smile on these children's faces and to enable healthy, happy, productive communities and countries. Thank you.
Thank you. Two very quick things. I mentioned that over the last decade, a lot of millions and millions of dollars had been spent on this problem, and it took our scientists $45,000 in 3 months to solve this. It goes to demonstrate the power of this. So next, I'll invite my colleague, Susan Addy, to talk about a host of things she's doing on one of the most precious things on our planet, which is water.
Good evening. I know we're running a little long, so I'm going to try to talk a little fast and cut it a little bit short. Oops. I'll start by going the right direction. So we know in 2012, around 900 million people don't have access to what's called an improved water source. That basically means they're drinking their water directly from rivers and streams untreated. Now, this wouldn't be such a problem, except that another 2.5 billion people don't have access to sanitation. It's about a third of the planet. Or, yeah, a third of the planet. Now, if you don't have any access to sanitation, you're stuck going in open sewers or fields or the same rivers, lakes, and streams where you get your drinking water. In fact, to understand what the meaning of sanitation is, you can think of it as what it is, which is any barrier between your poop and your drinking water. Now, that's a pretty important barrier, right? A third of the planet doesn't have that, so you can imagine what happens. Now, this doesn't just make us queasy, it's also really bad for health, because there are all kinds of pathogens that reproduce in the human gut, and those also come out in feces. Things like the bacteria that causes cholera, or various kinds of viruses and protists that lead to severe diarrhea, or even all kinds of parasitic worms that cause malnutrition and stunting. Now, these come out in the water when you don't have that barrier. You also don't have a barrier between these and your drinking water. This is mostly felt by children under 5. Every year, around 2.2 million children die of diseases that could be completely prevented with adequate water and sanitation. It's about 6,000 a day. So in the last 24 hours, the number of children who died of these preventable diseases could fill 12 theaters the size of this one. It's quite a lot. Now, keep in mind we're making a lot of gains. 2 decades ago, it would have taken 27 theaters to hold the number of children. So some things are being done. It's a good statistic, right? You've been hearing all these bad statistics. You can hear that some things are being done. But the number is still too high. And things are failing too quickly to really make a difference. So this leads to the question of why. Why are things failing? Why is it that in 2012 we can put somebody on the moon many years ago, but we can't solve water and sanitation for a third of the planet? Now, this is a question that's really interesting to me, and it's a really important question to answer. It turns out that a lot of really talented and smart people have tried to solve this problem. And they've come up with a lot of really innovative solutions, but those solutions are failing too fast to make a difference. For example, these are all decentralized water treatment systems that I've come across in India. Every single one of them works really well in a lab, and every single one of them appears to be very appropriate for the environment in which it's in. Every single one of them was defunct in less than a year. Now, I didn't try to find defunct systems. I literally couldn't find one that was working. Now, there are some that work, I'm told. I'm sure that it exists, but I haven't found any. So why are these all failing? Well, let's look at a couple of just quick examples. This is a filter system that was put in by a government. It was given to the village for free, and the government hired, as part of the implementation, somebody to come around every 6 months and change the filter media. The community used the filter, 6 months went by, the filter clogged, nobody came around. Now, they're not paying this person's salary, so they don't have any way to hold this person accountable. They don't have any way to contact the government, who is paying this person's salary. So the filter goes defunct, and they end up abandoning it, going back to their previous water sources. This is a pond sand filter. It was donated by a nonprofit organization, free of cost to the community. And this time they trained someone in the community to do the to do the maintenance for it, so that they wouldn't have to rely on someone outside of the community. That worked great for about 8 months, and then something broke that person couldn't fix. They didn't have anybody to call, they didn't have the internet, so the thing went defunct, and they went back to their other water sources. This is a dug well. It was donated for free to the community by a nonprofit organization. It was working really well for a while, but then somebody decided they needed a part that was in part of the pump, and that part kind of walked away. Now, the people who were still using it didn't have the money to replace this part, and they didn't really have the incentive to replace it because they didn't really like the taste of the water, so they ended up abandoning it. You can see a common theme here. right? The technologies themselves are not failing. The technologies themselves work in theory. What's failing is the system for maintenance, the system that's put in place to replace a part when it goes bad, to replace it when it goes missing, to keep it from disappearing in the first place, to do routine maintenance. These things don't exist. And that's what's happening to all of these filters. So we decided to think about things a little bit differently. We decided to look at the system of supporting the technology as being as important or even more important than the technology itself. So imagine you live in a village, and imagine that instead of a donated community system, I build for you a clean water store. Now, you don't have to do any maintenance. You don't have to use it if you don't want. But anytime you want clean water, you can go there and pay for it at a price you can afford. Even though you make less than $1 a day, you can afford the price. The government owns the infrastructure. The local government, the government that you elected and that you might know personally, a private company runs the system. Now, you don't know the private company, but they have access to global supply chains. They have access to professional quality control. And most importantly, they don't get paid unless they produce clean water that you're willing to pay for. So there's some accountability there. This is the model of something called Water Health International. And this is a picture of one of their centers. And they sell clean water for about 2 cents per 10 liters, which you can afford if you're making less than $1 a day. And they deliver it to your door for 4 cents per 10 liters, because people don't like to carry water. If you've ever carried water, you know that this is very, very true. Now, they started a few years ago. In January, they opened their 500th center, and they now claim 5 million customers per day. 5 million customers per day. Now, at a number like 5 million, you can start to make a dent in that 1 billion people without access to clean water that I mentioned earlier. You can't make a dent with donated systems that are failing, 80% failing within a year. So this is something that's working. Now, I haven't told you the whole story, though, because I've told you about the model, and even though I've made a case for why the model is incredibly important, you can't do this model without the right technology, right? You can't make this work unless you have a technology that operates so cheaply that you can sell it at a locally affordable price and still pay for the maintenance, and still fix it when it breaks, and still make a nice building, and still pay for quality control, and all of these other things, right? So that technology didn't exist in the mid-90s. And that's when Ashok Gadgil, who you saw speaking earlier about the Darfur Stove, started working on this in nights and weekends. And what he came up with was this. It's called UV Waterworks. I was supposed to have a demo here. That's my fault, I'm sorry. But it looks like that. And what UV Waterworks does is it takes UV light and it cripples the DNA in living things so that they can't reproduce. It's very energy efficient. It's very cost effective. It's very effective in the sense that it meets international standards and kills all the pathogens. And it's very elegant because you don't have to add any chemicals to the water, and you don't have to add a filter that might clog. It's also very cheap. It costs about 5 cents a ton, or 0.005 cents per liter. That's about 25,000 times less than the last bottle of water you probably bought. And it's about 6,000 times less than the bottle of water that would be for sale in a developing country. So now you've got something that will work in this model. Now you've got something that you can provide water that you can sell at a locally affordable price. If you can't sell it at a locally affordable price, you're not providing access, right? It doesn't matter what you're doing. So this was a big breakthrough. It's not something you would normally think of as an appropriate technology for developing countries, right? It doesn't look like the dug well, which looked much more appropriate in your mind. But this has reached orders of magnitude more people than the dug well, because this is partnered with a sustainable delivery system. They go hand in hand. The model doesn't work without the technology, and the technology doesn't matter without the model. So there's this pairing there. Now, when this was successful, we wanted to apply it to some other problems, namely arsenic in groundwater. It turns out that in a lot of developing countries, especially Bangladesh and West Bengal, they don't get water out of rivers and streams. They use hand-pumped tube wells like this, and they collect groundwater. Now, in many areas of the world, there are natural deposits of arsenic in the groundwater. This is the same arsenic you've heard of as a poison. It's the same thing that's in rat poison. And the reason it's a famous poison is because it's colorless, tasteless, and odorless. So right now, around 60 million people in Bangladesh and West Bengal are drinking water that has a poison they can't see or detect in any way. It's been called the largest mass poisoning in human history. And it's been going on for about 20 years. Now, when you drink small amounts of arsenic for a little while, you start to get lesions on your hands and feet. And those lesions can crack and form gangrene, which can lead to amputations, which in these areas tends to be a little bit ad hoc, so they have a high level of complications. Eventually, you can get internal cancers, which you can't detect because you don't have any of the modern detection systems that we have here. So that leads to a high level of fatalities. So this is a very insidious poison. It's an insidious problem that builds up over years. This is literally an invisible thing. Nobody can see it. We want to use a similar model to water health, but we want to make one key change. We want to partner with schools. The reason for this is because schools are a center of education, and education is going to be key for this problem. This isn't replacing river water with clean water that also tastes better. This is replacing clear, tasty water that you get in your backyard for priced clear water that you pay for 10 blocks away, right? Or get delivered to your house for a fee. So we have to inform people. People have to understand the importance of it to create value. And they should be able to decide if it has value for them or not. But school is a good way to teach what we know about arsenic and why it's important to use different methods. But again, just like with the UV waterworks, this model isn't going to work unless we have the technology to go with it. UV waterworks doesn't work because it kills living things and arsenic isn't living. So we're going with something called electrochemical arsenic remediation, or ECAR. ECAR is based on the fact that if you put steel in water, it rusts. If you put 2 pieces of steel in water and you run a little current through it, it rusts a lot, and it rusts really fast. It turns out that rust likes to absorb arsenic, and rust likes to gather other pieces of rust together and make big pieces of rust. So we put a lot of rust in the water. It mops up all the arsenic and grows into a big particle. When the particle is big enough, it sinks to the bottom, and we can take the arsenic-free water off the top. It's a very nice, elegant solution. It also costs a fraction of a cent per liter to operate. It's very low maintenance. It's very robust. And the supply chain is literally mild steel that you can get anywhere plus a little bit of electricity, which you can get from a solar panel or a battery. So it works really well. We've been developing it for about 6 years. This is a 600-liter prototype that just a few weeks ago we installed in this school outside of Kolkata. And I'm going to be visiting it in about a week, and it's got excellent initial results. It's producing water that's maybe 60 times the World Health Organization's safe limit to water that's below the safe limit. And we're going to run it for a few months and see how it goes. And you can follow it on our website, which is gadgillab.berkeley.edu. I don't know if they're going to get that later, but we'll get it to you, or you can find me afterwards. Now, the next problem that we want to tackle is brackish water. Brackish water is water that is not as salty as seawater, but it's too salty to drink. It tends to occur in areas where fresh water meets salt water and in some kinds of groundwater, and it's going to become much more important as we continue to deplete our fresh groundwater resources and as sea level rises and salt water intrudes into the groundwater resources we have. In fact, it's going to become really essential that we be able to treat brackish water and use those water resources. We've come up with a concept called capacitive deionization. It's in the conceptual stage, and we're working on the same kind of model that you've been seeing throughout, building a technology that can operate so cheaply and robustly and low maintenance that it fits inside a sustainable delivery model. And I'm going to stop there because we're a little short on time. So thank you very much.
Thanks, Susan. So you can imagine the value of desalination, taking all this water that's not quite as salty as seawater, but still too salty for consumption, and making that potable and usable. Our last technology we'll discuss today is with the problem of tuberculosis, TB. And for that, I have Aditya Katamanchi.
All right, so thank you all for coming and for paying attention for us going over time. So today I'm going to talk about tuberculosis. Tuberculosis is a very old disease. In fact, it's been with us ever since humans have been on this earth. It's a disease that affects the lungs. It's caused by a bacteria. And people who develop tuberculosis usually present with several weeks or months of cough, fever, weight loss, and night sweats. As the disease progresses, it starts to destroy the lungs, so patients often develop, they often cough up blood, and it's quite dramatic. Patients also lose weight profoundly, and the disease was actually called consumption for a long time because people sort of just waste away. The paintings shown here were done in the 1800s. The one on top is by Edvard Munch, and it depicts his sister who died of TB. And the one on bottom is by Claude Monet, who shows his wife dying of TB. At the time these paintings were done in the 1800s, 1 out of every 4 people in Europe who died of TB, right? And that's pretty astounding. So fortunately today, TB is much less common, especially here in the US and other parts of the developed world. But it still remains an important disease in much of the developing world. The areas shown in dark blue on the map on top are the areas where TB is really common. And the map on bottom here sort of blows up those countries based on the size of the countries is based on their TB prevalence. And you can see that TB disproportionately affects poorer parts of the world. Last year, there were about 12 million cases of TB worldwide, and 80% of those were in Africa and in Southeast Asia and in countries like India and China. There were about 1 million deaths from TB worldwide, and again, 80 to 90% of those were in sub-Saharan Africa. Another reason we should care about TB is really that TB, even though it's not common here in the US, TB anywhere is TB everywhere. And by that, what I mean is TB is spread when a person with the disease coughs and spreads infectious aerosols into the air. These aerosols can remain suspended for long periods of time, and when they're inhaled by other people, those people can then become infected with TB and develop the disease. So this can happen almost anywhere. It can happen to any of us. It can happen on a bus, on other forms of public transportation, in a crowded market, or even in a routine office building. Another reason that we remain concerned about TB, even here in the US, is the growing problem of drug resistance. In 2000, there were 10,000 cases of drug-resistant TB reported worldwide. But just 10 years later, that number increased to 650,000 cases. Drug-resistant TB is very difficult to treat, often taking 2 years of treatment with injections with very toxic and expensive medications. It's even been described by the US intelligence community as a national security threat because we really don't have any medicines to treat it. So preventing the spread of drug resistance is a key global health priority. The best way to prevent the spread of TB is to diagnose it early and then to start effective treatment. The picture here is of Edward Koch, the scientist who first saw TB under a microscope in the mid-1800s. And then fast forward 150 years later. And today, this is still how we diagnose TB in much of the world. A patient spits into a cup, a lab technician stains the slide, a lab technician then looks under a microscope and tries to look for these same organisms that Robert Koch saw in the 1850s. So after 150 years, really not much progress in the way that we diagnose TB. And the reason is because really we use microscopy because it's very fast. It takes about 2 minutes to make a slide and to look for TB under it. It's also very cheap. It costs less than $1 a test, and it's simple. It doesn't require any sophisticated equipment. But the problem is that microscopy is not very accurate. It misses about 1 out of every 2 cases of TB. So half of the people with TB don't have a positive microscopy result. It also doesn't identify drug resistance because TB that is sensitive to drugs and resistant to drugs looks the same under a microscope. So in the US, in addition to microscopy, we do culture, which means that we take a sputum specimen and plate it on a petri dish and wait for the TB bacilli to grow. Now, this is very accurate. Right? It's actually the most accurate test that we have for TB. But it also identifies drug-resistant strains of TB. But the main problem with this test is that it requires expensive biosafety infrastructure. I already mentioned that TB is highly infectious. Right? So when you're growing TB and growing it in large quantities, it exposes healthcare workers to a risk of acquiring the infection. So these are done in sort of biosafety level 3 facilities, which, as you can imagine, are very uncommon in the developing world. More recent tests, like PCR, are also very effective. They're highly accurate and they're rapid. They're providing results in 1 to 2 hours. But these have some limitations, right? They're not that simple to do. They require a little bit of sophisticated laboratory infrastructure and trained laboratory technicians. They also are moderately expensive, costing about $10 to $50 per test. And they can identify sort of a resistance to a single drug or a single mutation that causes drug resistance, but they're not very effective. The current platforms are not effective at identifying all of the different mutations that cause resistance to the various drugs we use to treat TB. So we're still looking for an ideal test, one that's accurate, it's fast, it provides results to clinicians right away, it's simple to do so that it can be done in any lab or in any clinic in the developing world, it's inexpensive so that its reach is far, and then it can identify which drugs the patient's disease is sensitive to. So not that we just start any treatment, but that we start effective treatment for the patient. So to address this problem, we're bringing together scientists from 3 leading institutions in California, the Berkeley Lab, the UCSF School of Medicine, and here at UC Berkeley. So we're going through a process where we're assembling technologies and expertise at each of these institutions to figure out how to address this problem of TB diagnosis. So the first piece of this solution is based on a technology called microfluidics, which deals with the behavior and control of fluids in very small spaces. And by small, I mean really small, sub-millimeter spaces. And so a technology was developed here at the Berkeley Lab, at UC Berkeley by Professor Luke Lee, which takes a sputum sample that's in a cup. A reagent is added to that sputum sample to decrease its viscosity. And then the sample is loaded onto a microfluidic chip. And what this chip does is it contains thousands of little channels or tubes. And it delivers the sputum sample to, say, a DNA detection platform. And the tube is coated with reagents, which extract DNA from the cells inside the sputum sample, and then deliver that DNA to sort of a detection platform that I'll tell you about in a little bit. The next step that we're going to take is take advantage of advances in genomics. This is what's pictured here is the entire genetic sequence of Mycobacterium tuberculosis, which is the organism that causes TB. This was first discovered or first reported in 1998. At our lab at UCSF, we've now sequenced hundreds of TB isolates from clinical isolates that were collected from patients enrolled in studies around the world. So what this allows us to do is to compare the genetic sequence of all the TB strains that we have to find targets that are common across all the different strains in the world. And then we can also compare these strains, the sequences of all other organisms, right? So we can really identify genetic targets that are specific for Mycobacterium tuberculosis and that are present across every TB strain. We can also then take drug-sensitive and drug-resistant strains and compare their gene sequences. And then we can figure out what are the mutations that cause resistance to all of the key anti-tuberculosis drugs. So the next step, once we have targets to go after, is then to develop a platform for detecting those targets. And for that, we're going to take advantage of a technology developed at the Berkeley Lab initially by Professor Gary Anderson. So what it is this little chip. It's a disposable plastic chip that I can keep in my pocket and hold in my hand. And what this chip contains is up to millions of features. And each feature contains millions of probes. And those probes, what they do is they go and find genetic targets, DNA targets. So this thing was initially designed to find for applications that require simultaneously detecting millions of different genetic targets. We're not interested in that many. There are probably about 100 or so genetic targets we need to identify in order to figure out whether someone has TB and whether they have TB that's resistant to one of several drugs that we use to treat TB. So what we do is led by a team of scientists both at the Berkeley Lab and at UCSF, Drs. Owen Brody, Susan Lynch, and Ulas Karoz. What they're doing is they're going to take all the genetic targets that we identify through our detailed genetic analysis of TB strains and load those targets onto this chip, so that just with this little device, this little disposable device, can contain all of the genetic targets we need to diagnose TB. The other advantage of this chip is that once it's designed, it's very inexpensive to manufacture. Right? For every target, it just costs pennies to place onto this chip. So for about 100 targets, a chip with 100 targets can be manufactured for just a few dollars. And the last technology we're going to take advantage of is called CellScope. Right? So once we have all of these PCR reactions happening on this chip to identify genetic targets, we need a way to read and interpret those results, like which ones are positive, which ones are finding the targets. Right now, that takes expensive equipment and sensors to do that. But instead, we're going to take advantage of a technology that Dr. Fletcher developed here at UC Berkeley. And what this is a cell phone. Right? It uses the cell phone and the computing power of a typical smartphone, the camera and the computing power of a smartphone, and connects that to an optical chamber to process light signals. So what's shown here is a simple microscope. You have mirrors and lenses which draw light to the camera of a smartphone. And this now is just a simple microscope, simple and inexpensive microscope that functions as well as some of the expensive microscopes that are in many labs today. Dr. Fletcher and his team have also shown that this device can be used to process the light signal from a PCR reaction, which is what we use to identify DNA targets. So what we need to do now is to develop this technology further to be able to simultaneously detect and process the signals from the hundreds of PCR reactions that will be developed onto this chip. But what this does is provides a very inexpensive and portable platform for us to be able to detect the PCR reactions occurring on our TB chip. So this is what we hope it'll look like. A doctor collects a sputum sample from a patient. A simple reagent is added to decrease the viscosity of the specimen. The specimen is loaded onto a chip, which extracts and delivers the DNA to this little microchip. And the microchip is placed into a simple reader based on a smartphone. right? And then within an hour, a doctor and a patient knows whether he or she has tuberculosis and whether that tuberculosis is resistant to key drugs. So these are the types of technologies and innovations we hope to bring to this problem of tuberculosis, to find a diagnostic that can really help any patient in the world know whether they have TB and to start effective treatment right away. Thank you.
You have the chip. So this chip, it's got this tiny space here. It can identify, if you put water in it, it can identify one of 8,000 bacteria. If you fall sick in a developing country, you have fever, you have no idea what's wrong with you. Do you have malaria? Do you have TB? Something else? Unclear. And while you're waiting to find out, you could die. Can we take this and repurpose it so that with a single test, you can actually figure out which one of those diseases you have? So you've seen a sample of the kinds of things we can do, we're hoping to do. This is the world's largest repository of science like this. We have our work cut out for us. So, thank you.
So we told you that the program was going to run long, but we have so many stories to share. We wanted you to hear as many as we could reasonably crowd into this format. If you just bear with me for a second, we're going to put some chairs out. We'll bring everybody back out, and we'll have our question and answer period. Looks like we only have one person over here on mic 1.
So hunger and disease are obviously a great threat to the developing world, but overpopulation might be a greater threat. And as harsh and brutal as it may sound, death from hunger and disease sort of serves as a natural population control, especially in areas where there's a historical and cultural preference for large families and where there's no strong central government like China does, where you can impose a one-child policy on its population. So with all the robust and durable technologies that the scientists are building, are you all concerned that this might inadvertently lead to further overpopulation beyond what the Earth can sustain?
This is a deep philosophical question that someone above my pay grade should answer. But one way of thinking about it is this, right? Which is everyone deserves a fair shot at a healthy, productive life. And will the world be better off if more people live longer lives? Will the world be better off if everybody consumes more? Right? Obviously, the latter is difficult, but I think our responsibility as global citizens is to make sure everyone has a decent shot at this.
I think there's a corollary to that question, which I'm just going to ask. We did receive some questions on social media, and there was sort of a recurring theme. Well, poverty in the developing world is an important problem to solve, but what about America? So, Shashi, what about American poverty?
Poverty, ill health, poor education, this happens everywhere in developed and developing countries. And I think trying to solve those in one part of the world is not mutually exclusive of trying to solve it anywhere else. Certainly, we believe that not enough of it is being done in the developing world. And so we're certainly hoping that a lot of this stuff can be equally applicable to problems here. We've cut off our slice of that problem at the LIGTT Institute and are focusing on the poor countries where nobody else is looking.
Okay, mic 2.
Thank you. Drawing on that, which had some flavor of unintended consequences, I think what most has my attention is like systems theory, which I'm sure there's a lot of systems theory behind all your thinking. The biggest view possible on a problem. When I was looking at things like the uterine atony and then the infant warmers, I was just concerned about some unintended consequences of the infant warmers, that they may be construed as being better than the skin-to-skin model. So those kind of cultural things, like where the 3-rock stove seemed kind of sacrosanct in a way, but the skin-to-skin seemed to be somewhat less culturally fundamental somehow. Yeah, so that was one thing. And so kind of the same thing on the uterine atony, like I never heard like, put baby to breast, best first route to uterine atony, I would think. So just sometimes it seemed like that the most natural solution wasn't as underscored as I would have loved to see. That's my only. So I just love response about that, because I'm sure it must come into the thinking. So when you do all that, what's most important? Who keeps sounding the bass note of what is most important? Or,
Thank you. So I'll pass this question on to Roger, but we'll say that in this particular case, we were explicitly asked by the Ministry of Health in Rwanda through our partners in health. And our basic philosophy is, if somebody doesn't ask for it, we won't do it. The demand has to exceed our willingness and our desire to do it. So Roger, you want to share a couple of thoughts on how we're working with the ministry?
Yeah, I don't have much more to add, but I'll just say that, like Alyssa mentioned, kangaroo care or skin-to-skin contact is obviously the preferred method, and that is widely used, and it should be encouraged. But there are occasions, as Alyssa mentioned, when that's not possible. The mother is ill, or during transport, chaotic transport. So there is a role for a appropriate infant warmer, we think, and indeed the government of Rwanda thinks as well. So we do think it's an important technology, but certainly no replacement for skin-to-skin contact.
I definitely got the part where the mother was ill or deceased. I didn't get the travel part so much, but then just the same with the oxytocin or the Pitocin. Is there also, I just missed any part of the first route might be to put the baby to suckle. Is that not a cultural?
So the question of unintended consequences is extraordinarily important, and for every single project we do, before we launch it, we will and we are rigorously evaluating what the possible consequences are, and we're monitoring it very closely. So it's a very important question. Thank you for asking that.
Okay, thank you so much.
We have a question from this mic over here.
I'm kind of wondering about that infant warmer also. Is it necessary to heat it up above that body temperature in order for it to cool down to work?
Roger.
Yeah, well, to melt the wax, the water will need to be warmer than 37 degrees, and the warmer the water is, then the faster the wax melts. So there's trade-offs involved, but basically to melt the wax as quickly as possible, the water would be warm, warmer than 37. But then as long as there's a mechanism to make sure that when it enters in contact with the baby, then it's at 37, then that's important.
Well, how fast does that pad have to heat up to be useful?
Well, that's a good question. There will be different applications. If it's used in a hospital setting, there might be multiple warmers available for use, and if it's used, for example, by a midwife when she's traveling to a mother's house to give birth, then she may choose to warm it up before the delivery and keep it inside of the thermos bottle, keep staying warm until after the delivery when it's needed. That would depend on the application.
Thank you for your question. Another question over here, please.
Sure, this takes off a little bit from those questions. Successful.
I'm sorry, ma'am. We're running late, and we have a number of people.
Pad can't just be put against an adult's body so that the body temperature would heat up that pad to whatever temperature it needs to be.
That would work, but it would take a long time to warm up the pad.
Well, that's what I wondered, how fast you needed it to heat up. Thank you.
Thank you. Yes.
Well, I'm also interested in the successful deployment and use of your technologies, and I know it's really, really difficult to do on the ground, and it seems you've found wonderful partners at the local level, and I'm interested in beyond the ministries of health, what partners are you finding, how are you finding them, and what is your ideal vision for developing this aspect of your work?
Great question. We absolutely believe that there's only a part of the problem we can solve in Berkeley, California. we are focusing on countries where we have access to a significant partner who will allow for not just distribution, but product design and development. So I'll give you a couple of examples. In Bangladesh, for instance, there's a very large NGO called BRAC, which is credited, it's considered by many people to be a parallel government. They're credited with rebuilding a good portion of Bangladesh after the 1972 civil war, which led to the creation of the country. So the advantage of working with an organization like BRAC is they have extremely deep roots. They are a Bangladeshi organization. They can give us guidance on what to do, how to do it, how to deploy it, and they'll end up owning the business model. Another example, and I won't name the organization because we're still in discussions, but it's in Nigeria. And Nigeria, as many of you may know, it's a very difficult place to get a lot of stuff done. And we're working with one of Africa's leading philanthropists who set up a foundation over there. And what their philosophy is that you can build the core technology in the US, but we have to have local entrepreneurs, local business people, local companies that actually benefit from this. So there's actually job creation and employment base that comes out of it. We fully subscribe to that model and believe that if somebody ideally local is earning a living out of it, then it'll lead to a more sustainable business model.
Thank you. A question from mic number 1.
Yeah, this goes directly to your question about, or the one raised about partnerships. So whom did you include when you went through the iteration of outlining the issues, the problems, the big issues? Who are the partners outside of this organization? As you say, the ones who are going to be your partners on the ground, were they included in that assessment? And how are you planning to, in the future, maybe if there's another cycle of problem assessment, are you going to include them? Are you actually, is there a way to scale that in such a way that you'd get more partnership feedback into this? I know maybe the organization is kind of the choke point, but is there a thought about expanding the number of people who actually have input into what you guys are doing?
Zach, Lena?
Sure. So the initial set of buckets that we developed was based on the Millennium Development Goals and the Human Development Index, and which were generally agreed upon by large parts of the community. And essentially what we do, and we simplified very much as we were talking about it because we didn't have very much time, but we're engaging in interviews with a large number of experts, the goal being, one, to vet our analysis and to get their expertise, but to also see what we're missing. And the whole way that we're setting up this process is that it's iterative and it's based on feedback. So if it turns out that we've missed an area, or if there is some sort of a cross-cutting theme that begins to emerge, or we identify something that is a major issue that initially we hadn't thought was an issue, we're flexible to incorporate that. So I think your point gets to something that's very important, which is being responsive to the people who understand the issues best, and that's absolutely how we're trying to structure it.
So just a small follow-up. In terms of the work that you guys have outlined, would we see a sort of feedback in terms of efficacy of what you're trying to, the solution in like a year and a half, and how will that be broadcast?
So I would say there are two elements there, right? So a large part of what we do is develop and deploy technologies, which you heard most of the people up here talk about. And those are absolutely technologies that we plan to evaluate in terms of effectiveness. Were we able to achieve our goals? Were there any unintended consequences? And we plan to be open and transparent and use that to inform our projects going forward. As far as the 50 breakthroughs analysis, which Lena and I spoke to, we plan for this to be a living document. We don't want it to be a report that's published once and then just sits there. So the goal is to, on an annual basis, refresh it. We hope to have events where people will be able to come in, and we can talk about what progress we've made towards these goals. Are the major problems that we see still the biggest problems facing development? And we expect that if we're doing our job and other people are doing their jobs, they'll change and they'll evolve. So both of those have formal development cycles that we plan to go to, so we can continuously learn from what we're doing and what we're hearing.
Thanks for your question. Another one over here.
Yes. Well, thank you very much, all of you, for a very enlightening presentation. I know Lawrence Berkeley Lab has traditionally had a different mission. So I'm going to ask a three-part question, if you don't mind. I'd like to know how difficult was it to pull the team together and take on these noble projects? What is your source of funding? You still get work with DOE or other sources? And whether or not we are going to see similar trend in other national labs, similar to what you are doing.
Good. I'll take a crack at the first two and ask Jeff to pitch in on the third, or we can just punt on the third. There's a long line of scientists and engineers at the lab who are tremendously excited to work on this. In fact, a good chunk of my time is actually spent understanding what their background is, what they're interested in. And the supply far exceeds the demand right now, just given the things we can take on. So the least of our problems will be the willingness and interest from the scientists and engineers. Funding, the lab has given us a small amount of seed funding, and then we are actively talking with a number of funders in different parts of the world. Again, I do not believe that funding, I don't believe that funding will be the biggest problem. There are many, many bigger problems in terms of developing really valuable breakthroughs and then deploying them. And hopefully the funding will come through fairly soon.
And your last question was about our involvement with the other labs, was that?
Other national labs, are they pursuing similar paths or not?
We believe in collaboration.
Okay.
Next question, please.
One of the things that strikes me about all of this is how all of these solutions have to work in environments that are completely different from the one that we live in. And I'm wondering how hard it is to keep, let's just say, inappropriate solutions from constantly entering your brain as you're working on a problem. I mean, does it help, for example, to go travel to the area where you're going to be, where the technologies are going to be used so that you can visualize it? I mean, how do you do that?
I'll ask Susan to talk about her experience in water.
Sure. I think that that's a great question. I think that traveling to the area is a really good way to start. It's also talking with people who have been working on the issues and have experienced the failures again and again. A lot of times you'll find in communities people have tried a lot of the things that you'll go there thinking is a brand new solution, and people have tried it and discarded it for various reasons. The other thing is just being able to prototype a lot and to be able to present a lot of solutions and to put them in practice a little bit, do a field trial, see how it works, get a lot of people talking about it and get a lot of feedback, and doing this constant iterative process. And so all of these things help a lot. And at the end of the day, you don't decide what the final design is. The people decide what the final design is because they either accept or reject what you've given them. So that's what I would say.
Thank you for your question. We're going to take a couple more. And I encourage you, if we don't get to everyone tonight, you can leave your questions on our Facebook page, or you can email Public Affairs. There are lots of ways to reach us, and I promise we will get the answers to you. So next question, please.
Well, again, thank you. It was a very interesting and informative talk you guys all gave. My question is actually more, I guess, about each of you, in that it sounded like the LIGTT Institute began as a place where people were almost volunteering their time in projects that they found interested. Is that still how it is? Do you all have separate work that you do, separate research that you work on, and is this a side project or is this full-time? And so interested to know about more of the backgrounds of how you all got to the particular projects you are working on now.
Great question. The decision, when we decided to create the institute, the commitment was this cannot be done nights and weekends. It has to be a full-time commitment. And there's a slight variation to that, which is that we have a core team, a lot of the people sitting here on stage, where it's our day job, and it's a night job as well, which is wonderful. And then we have project teams, and for each project, depending on the complexity of the project, it may take 100% of a scientist or engineer's time, it may take 25%. And that will vary based on how much time they need, whether they feel they need to stretch it out or compress it. But the point is, A, it's not volunteer, B, it is a serious commitment, often full-time.
Thank you. Last question.
Thank you for your presentation tonight, very informative. Just a quick question, wondering how often intellectual property issues crop up other than just in public presentations?
Great question. As Jonathan was saying, you know, we got advice from our legal team not to share too much. And here's the reason, which is that our business is to come up with these things for public good. We are a public institution. Our mission is the global development good that will come out of this. Having said that, it's not clear that everyone is motivated by the same thing in other for-profit and non-profit institutions in different parts of the world. So the problem we're trying to avoid is somebody else replicating this, patenting it, and essentially closing out the market to those who may actually provide the public good. So we're protecting this IP to make sure that it reaches the people who it's intended to reach.
So that concludes our presentation for the evening. Thank you, audience. Thank you, presenters. We'll have a full slate of Science at the Theater in the spring of 2013. Please look at the Friends of Berkeley Lab website. Thank you again for coming.